Yeah, welcome to Easy Mathematics and a new video for the JEE exam, the advanced. Today we want to solve question 8 from 2019 sheet 2. And like the other videos, if you haven't seen them, first I want to talk about general hints, and then we will discuss question 8. So let's go. First of all, yeah, it sounds stupid, of course, when I say read the whole task carefully. What I mean by that is, if you read the question, think about the given conditions. What do you know about them? What might help? And it's also a nice try if you take a look at the answers. Sometimes they tell a lot about the solving strategy. Okay, also in this case, in question 8, we will see how to make advantage of this. Okay, and yeah, how to prepare. Of course, you should know standard techniques, geometric series, telescoping, sums, let's write sums, system of equations, trigonometric identities, matrix properties, stuff like that, and also basic properties of concepts, for example, Riemann integral and other stuff. And most of the tasks, they look horrible, but the structure of the question gives you many hidden hints. Okay, if you think about it carefully, then the question is not that hard than it looks. Also in question 8, you will see that in detail. Okay, so where is question 8? Here is question 8. Okay, so question 8: for non-negative integers n, let f of n be the sum of a product of sines over the sum of sine squared of something. Okay, assuming the inverse cosine takes values in the closed interval from 0 to pi, which of the following options are correct? F of 4 is square root of 3 over 2. Sine of 7 times the inverse cosine of f of 5 is 0. If alpha is the tangent of the inverse cosine of f of 6, then alpha squared plus 2 alpha minus 1 equals 0. And fourth, the limit as n goes to infinity, f of n is 1/2. Yeah. Funny question, in my opinion. Let's see. Okay, we read carefully. It's about trigonometric terms, and of course what might help is of course trigonometric identities, or maybe because the values are small, maybe a direct calculation is also possible. And do we get hidden hints from the answers? Yes, we do. Why? We should try trigonometric identities. Why? Because our answers, we can easily guess what might happen. Look at this cosine inverse of f of pi. Okay. If this answer is true, we don't know yet, but if this is true, it might be possible that our f of x simplifies to some cosine blah 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 pi x or sine blah 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 pi x, so we can cancel inverse cosine and cosine. Okay, and for example, question 1, you can do it by hand, calculate all these products and summing up. This is possible. Why? Because if we plug in 4, then we get something pi over 6, and something pi over 6, these are nice values. If you look at 5, we get something pi over 7, and so these are not so nice values, so it's a good choice to try to manipulate this sum. Okay, and also this cosine minus 1, it's, yeah, maybe we get some nice function cosine blah 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 pi x, or maybe sine blah 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 pi x. Okay, and also what you also know, if 2 and 3 are true, 2 and 3, or maybe one of them is true, then we know 4 is false. Okay, so if f of x is really a single and easy cosine, then of course the cosine has no limit, so 4 is false if 2 is true. Okay, this is what we can see by the answers. And this question is also funny. Here is we have here f of 6, so we get here something pi over 8, and something pi over 8 is quite nice value. So yeah, this can be also true. Maybe we get a nice value and we can plug in. Okay, so yeah, we will see how to simplify this summation. Okay, if you think about, please stop the video and take a second to think about where you find yeah, products of sine. Okay, please pause the video and think about that. So if you are familiar with products of sines like sine x times sine y, maybe you have seen this formula. If you do not know it by heart, it's not a big deal. It's easy to prove. We will do that. You know, of course, cosine of x plus y, you get cosine of x times cosine of y minus sine of x sine of y. And for cosine x minus y, you get cosine x times cosine y plus sine x sine y. Okay? Yeah, and we are interested in sine x sine y, and to get this, we subtract 1 from 2, so 2 minus 1, and then you get immediately this identity. And if you look carefully in the denominator, we have sine squared, so we get the sine squared as a special case for x equals y. Okay, so with these identities, we plug in carefully in our f of x, and we get this function. Okay, so make sure that you get it also. Okay, so just plug in the values x and y carefully, and you should get exactly this. Okay, and the next step is, you see in the numerator, if the first cosine is not depending on k, so we have from k to 0, from k equals 0 to n, we have n plus 1 cosines. This is this part, and we are left with the sum of these cosines. Okay, and also in the denominator, the 1 is not depending on k, so we have a bunch of 1s. How many? N plus 1 minus the sum of these cosines. Okay, and now you should think about how to manipulate this sum. And yeah, if you have a sum of sines or cosines, it's it's a nice identity for this is, here we will use this fact. if you wonder where does this come from, you can prove this with the complex E function and write the cosine in terms of complex E functions. Then you can use the geometric series and then you get this result by the geometric series. Okay, you can prove this also without complex numbers by using a nice identity which is in the form of this identity. Then you switch the order and you get this result also. Or if you can guess this result, then of course you can try to prove this via induction. There are many ways to get this. I will not do it in detail. Like I said, I guess the most easiest way is to use the complex E function. The other way, it uses a nice telescoping property, but it's not so obvious in my opinion. I leave the details for you, but we will use this effect. Okay, and if you plug in all the values carefully, you get this. It looks horrible in the first moment, so take your time and look carefully. Okay, so we're just plugging in all the values and we get to this result. What can we do with this stuff? It looks horrible, and yeah, what can we do? Please, before you come to the idea and to make the denominators equal, and so I would not recommend it. In such questions, it's often useful to use symmetry properties. Okay, and we look carefully. I explain it and I leave the details for you. The next step looks like this. Please pause the video and try to understand what happened, and when you come back we talk about it. Okay, so I hope you have seen what's going on here. It's a little bit tricky. First of all, look at this sign. This is n plus 1 over n plus 2 pi, and in the denominator we have sine of pi over n plus 2. If you use the symmetry property, I will write down what I have used here. What is here going on is this property. Okay, this is exactly what we used for these two signs. Okay, please look carefully and then you can understand why these are equal. Then we can cancel them and we leave with cosine n plus 3 over n plus 2 pi, and we write that as pi plus pi over n plus 2. Okay, and also here for the same reason we cancel these out, these two signs, and we are left with cosine of pi, and this is minus 1. Okay, then of course the next step is very easy. N plus 1 minus minus 1 is n plus 2, and cosine pi plus pi over n plus 2 is the same as negative cosine of pi over n plus 2. This is also one of the symmetry properties. Okay, and now this is very beautiful because we can factor out cosine pi over n plus 2, and we are left with cosine pi over n plus 2. Very beautiful. Okay, so the main step is of course this crazy summation. This is, if you don't know it, I want to repeat that. Okay, if you do not know this identity, use the complex e function to simplify and you will get this result also. Okay, it's not so hard. Use the geometric series and you get this result. Then the next important step is to use the symmetry of sine, and please make sure that you understand this. Then you will see that the sines, they cancel out and we are left with a bunch of cosines, and it simplifies perfect to cosine pi over n plus 2. Now we take a look at the answers and we see immediately f of 4 is true. We get pi over 6. Okay, this is clear. The second is also true. And like I said, this cosine inverse, it cancels this cosine and we get pi over 7. It cancels out with this 7, we get sine pi, and this is 0. Very nice. 2 is also true. For 3, this is also true. Cosine minus 1 of f of 6, we are left with pi over 8. Okay, so alpha is tangent pi over 8. And if you do not know that tangent pi over 8 is square root 2 minus 1, how can you see that? Use the half angle formula for pi over 4 over 2, and then you get this result. Okay, so it's not so hard, but what is hard in this question is you need a good view on the symmetry properties and stuff like that. Yeah, it's not so difficult. I guess we will agree. It's not so difficult, but it's hard to see in the first moment because of these bunch of cosines and the bunch of n plus 1, n plus 2, and so on. But it's not so hard, I guess, and therefore 3 is true. Yeah, you can easily check square root 2 minus 1 is a 0 of this polynomial. Yeah, and 4, if you take a look at cosine, if n approaches infinity, if cosine has no finite limit, so 4 is false. Alright, that was question 8. Yeah, for me it was a really beautiful task. I hope you liked this problem also. And again, what I want to mention is you should be familiar with some basic trigonometric identities. Okay, so I guess this question was not so hard after you see the solution. In the first moment also the answers look horrible, but do not be afraid of these crazy answers. See them as some hidden hints. They tell a lot about the structure of the problem and also what kind of strategy you should use to force this question. Okay, so thanks for watching. Have a nice day. See you next time. Bye bye.